Welcome back in part 4 of Google Chrome.
The private browsing feature, called incognito mode, prevents the browser from locally storing any history information, cookies, site data, or form inputs.
Downloaded files and bookmarks will be stored.
In addition, user activity is not hidden from visited websites or the internet service provider. Incognito mode is similar to the private browsing feature in other web browsers.
It does not prevent saving in all windows. You can switch between an incognito window and any regular windows you have open. You'll only be in incognito mode when you're using the incognito window.
The iOS version of Chrome also supports the optional ability to lock incognito tabs with Face ID, Touch ID, or the device's passcode. In February 2012, Google announced that Chrome would implement the Do Not Track (DNT) standard to inform websites the user's desire not to be tracked.
The protocol was implemented in version 23.
In line with the W3's draft standard for DNT, it is turned off by default in Chrome. A multi-process architecture is implemented in Chrome where, by default, a separate process is allocated to each site instance and plugin.
This procedure is termed process isolation and raises security and stability by preventing tasks from interfering with each other.
An attacker successfully gaining access to one application gains access to no others, and failure in one instance results in a sad tab screen of death, similar to the well-known sad Mac, but only one tab crashes instead of the whole application.
This strategy exacts a fixed per process cost up front, but results in less memory bloat over time as fragmentation is confined to each instance and no longer needs further memory allocations.
This architecture was later adopted in Safari and Firefox. Chrome includes a process management utility called Task Manager, which lets users see what sites and plugins are using the most memory, downloading the most bytes, and overusing the CPU, and provides the ability to terminate them.
Chrome version 23 ensures its users an improved battery life for the systems supporting Chrome's GPU accelerated video decoding.
The first production release on December 11, 2008 marked the end of the initial beta test period and the beginning of production.
Shortly thereafter, on January 8, 2009, Google announced an updated release system with 3 channels, stable, corresponding to the traditional production data. A developer preview, also called the Dev channel.
Where there were before only 2 channels, data and developer, now there were 3.
Concurrently, all developer channel users were moved to the data channel along with a promoted developer release.
Google explained that now the developer channel builds would be less stable and polished than those from the initial Google Chrome's data period.
Data users could opt back to the developer channel as desired.
Each channel has its own release cycle and stability level.
The stable channel updated roughly quarterly with features and fixes that passed thorough testing in the data channel.
Data updated roughly monthly with stable and complete features migrated from the developer channel.
The developer channel updated once or twice per week and was where ideas and features were first publicly exposed and sometimes fail and can be very unstable at times. Quoted
remarks from Google's policy announcements. On July 22, 2010, Google announced it would ramp up the speed at which it releases new stable versions. The release cycles were shortened from quarterly to 6 weeks for major stable updates.
Data channel releases now come roughly at the same rate as stable releases, though approximately 1 month in advance, while dev channel releases appear roughly once or twice weekly, allowing time for basic release critical testing.
This faster release cycle also brought a fourth channel, the Canary channel, updated daily from a build reduced at 9 o'clock UTC from the most stable of the last 40 revisions.
The name refers to the practice of using canaries in coal mines, so if a change kills Chrome Canary, it will be blocked from migrating down to the developer channel, at least until fixed in a subsequent Canary build.
Canary is the most bleeding-edge official version of Chrome and somewhat of a mix between Chrome Dev and the Chromium snapshot builds.
Canary releases run side by side with any other channel. It is not linked to the other Google Chrome installation and can therefore run different synchronization profiles, themes, and browser preferences.
This ensures that fallback functionality remains, even when some Canary updates may contain release-breaking bugs.
It does not natively include the option to be the default browser, although on Windows and OS X it can be set through system preferences.
Canary was Windows only at first. An OS X version was released on May 3, 2011. The Chrome Data Channel for Android was launched on January 10, 2015. Like Canary, it runs side by side with a stable channel for Android.
Chrome Dev for Android was launched on April 29, 2015.
All Chrome channels are automatically distributed according to their respective release cycles.
The mechanism differs by platform.
On Windows, it uses Google Update. An auto update can be controlled via group policy.
Alternatively, users may download a standalone installer of a version of Chrome that does not auto-update.
On OS X, it uses Google Update Service. An auto update can be controlled via the OS X defaults system.
On Linux, it lets the system's normal package management system supply the updates.
This auto-updating behavior is a key difference from Chromium, the non-branded open-source browser which forms the core of Google Chrome.
Because Chromium also serves as the pre-release development trunk for Chrome, its revisions are provided as source code and buildable snapshots are produced continuously with each new commit, requiring users to manage their own browser updates.
In March 2021, Google announced that starting with Chrome 94, in the third quarter of 2021, Google Chrome stable releases will be made every 4 weeks, instead of 6 weeks as they have been since 2010.
Also, Google announced a new release channel for system administrators and browser embedders with releases every 8 weeks.
Releases are identified by 4-part version number, for example, 42.0.2311.90, Windows Stable Release April 14, 2015.
The components are major.minor.build.patch.
Major.minor reflects scheduling policy.
Build.patch identifies content progression.
Major represents a product release.
These are scheduled 7 to 8 per year, unlike other software systems, where the major version number updates only with substantial new content.
miner is usually 0.
References to version X or X.0, for example, 42.0, refer to this major .miner designation.
Build is ever increasing.
For a release cycle, for example, 42.0, there are several builds in the canary and developer period.
The last build number from developer is checked throughout data unstable and is locked with a major .miner for that release.
Unpatch resets with each build, incrementing with each patch.
The first patch is 0, but usually the first publicly released patch is somewhat higher.
In data unstable, only patch increments.
Chromium and Chrome release schedules are linked through Chromium major version branch point dates, published annually.
The branch points precede the final Chrome developer build initial released by 4 days, nearly always, and the Chrome stable initial release by roughly 53 days.
Example, the version 42 branch point was February 20, 2015.
Developer builds stopped advancing at build 2311 with release 42.0.2311.4 on February 24, 4 days later.
The first stable release, 42.0.2311.90, was April 14, 2015, 53 days after the branch point. Chrome supports color management by using the system, provided ICC v2 and v4 support on Mac OS, and from version 22 supports ICC v2 profiles by default on other platforms. Color management is the process of ensuring consistent and accurate colors across various devices, such as monitors, printers, and cameras.
It involves the use of color profiles, which are standardized descriptions of how colors should be displayed or reproduced.
Color management is necessary because different devices have different color capabilities and characteristics.
For example, a monitor may display colors differently than a printer can reproduce them.
Without color management, the same image may appear differently on different devices, leading to inconsistencies and inaccuracies. To achieve color management, a color profile is created for each device involved in the color workflow.
This profile describes the device's color capabilities and characteristics, such as its color gamut, range of colors it can display or reproduce, and color temperature.
These profiles are then used to translate colors between devices, ensuring consistent and accurate color reproduction. Color management is particularly important in industries such as graphic design, photography, and printing, where accurate color representation is crucial.
It helps to maintain color consistency throughout the entire workflow, from capturing an image to displaying or printing it.
Parts of color management are implemented in the operating system, OS, helper libraries, the application, and devices.
The type of color profile that is typically used is called an ICC profile.
A cross-platform view of color management is the use of an ICC-compatible color management system.
The International Color Consortium, ICC, is an industry consortium that has defined
an open standard for a color matching module, CMM, at the OS level.
color profiles for
Devices, including device link profiles that transform one device profile, color space, to another device profile without passing through an intermediate color space, such as L asterisk K asterisk B asterisk, more accurately preserving color.
Unworking spaces, the color spaces in which color data is meant to be manipulated.
There are other approaches to color management besides using ICC profiles.
This is partly due to history and partly because of other needs than the ICC standard covers.
The film and broadcasting industries make use of some of the same concepts, but they frequently rely on more limited boutique solutions.
The film industry, for instance, often uses TaBNWNE's lookup table to represent a complete color transformation for specific RGB encoding.
At the consumer level, system-wide color management is available in most of Apple's products: Mac OS, iOS, iPad OS, Watch OS.
Microsoft Windows lacks system-wide color management and virtually all applications do not employ color management.
Windows Media Player API is not color space aware, and if applications want to color manage videos manually, they have to incur significant performance and power consumption penalties.
Android supports system-wide color management, but most devices ship with color management disabled.
Overview 1. Characterize.
Every color managed device requires a personalized table or color profile, which characterizes the color response of that particular device. 2. Standardize.
Each color profile describes these colors relative to a standardized set of reference colors, the profile connection space. And 3. Translate.
Color managed software then uses these standardized profiles to translate color from one device to another.
This is usually performed by a color management module, CMM. To describe the behavior of various output devices, they must be compared, measured, in relation to a standard color space.
Often a step called linearization is performed first to undo the effect of gamma correction that was done to get the most out of limited 8-bit color paths.
Instruments used for measuring device colors include colorimeters and spectrophotometers.
As an intermediate result, the device gamma is described in the form of scattered measurement data.
The transformation of the scattered measurement data into a more regular form, usable by the application, is called profiling.
Profiling is a complex process involving mathematics, intense computation, judgment, testing, and iteration.
After the profiling is finished, an idealized color description of the device is created.
This description is called a profile.
Calibration is like characterization, except that it can include the adjustment of the device, as opposed to just the measurement of the device.
Color management is sometimes sidestepped by calibrating devices to a common standard color space such as sRGB when such calibration is done well enough. No color translations are needed to get all devices to handle colors consistently.
This avoidance of the complexity of color management was one of the goals in the development of sRGB. Image formats themselves, such as TIFF, JPEG, PNG, EPS, PDF, and SVG, may contain embedded color profiles that are not required to do so by the image format.
The International Color Consortium standard was created to bring various developers and manufacturers together.
The ICC standard permits the exchange of output device characteristics and color spaces in the form of metadata.
This allows the embedding of color profiles into images as well as storing them in a database or profile directory.
Working spaces such as sRGB, Adobe RGB, or ProPhoto are color spaces that facilitate good results while editing.
For instance, pixels with equal values of R, G, V should appear neutral.
Using a large gamut working space will lead to posterization, while using a small working space will lead to clipping.
This trade-off is a consideration for the critical image editor.
Color transformation, or color space conversion, is the transformation of the representation of a color from one color space to another.
This calculation is required whenever data is exchanged inside a color managed chain and carried out by a color matching module.
Transforming profile color information to different output devices is achieved by referencing the profile data into a standard color space.
It makes it easier to convert colors from one device to a selected standard color space and from that to the colors of another device.
By ensuring that the reference color space covers the many possible colors that humans can see, this concept allows one to exchange colors between many different color output devices.
Color transformations can be represented by two profiles, source profile and target profile, or by a device link profile.
In this process, there are approximations involved which make sure that the image keeps its important color qualities and also gives an opportunity to control on how the colors are being changed. In the terminology of the International Color Consortium, a translation between two color spaces can go through a profile connection space, PCS, color space 1 to PCS, CIELAV or CIEXYZ. To color space 2, conversions into and out of the PCS are each specified by a profile. In nearly every translation process, we have to deal with the fact that the color gamut of different devices vary in range, which makes an accurate reproduction impossible.
They therefore need some rearrangement near the borders of the gamut.
Some colors must be shifted to the inside of the gamut, as they otherwise cannot be represented on the output device and would simply be clipped.
This so-called gamut mismatch occurs, for example, when we translate from the RGB color space with a wider gamut into the CMYK color space with a narrower gamut range.
In this example, the dark, highly saturated purplish-blue color of a typical computer monitor's blue primary is impossible to print on paper with a typical CMYK printer.
The nearest approximation within the printer's gamut will be much less saturated.
Conversely, an inkjet printer's cyan primary, a saturated mid-brightness blue, is outside the gamut of a typical computer monitor.
The color management system can utilize various methods to achieve desired results and give experienced users control of the gamut mapping behavior.
When the gamut of source color space exceeds that of the destination, saturated colors are liable to become clipped, inaccurately represented, or more formally burned.
The color management module can deal with this problem in several ways.
The ICC specification includes 4 different rendering intents, listed below.
Before the actual rendering intent is carried out, one can temporarily simulate the rendering by soft proofing.
It is a useful tool as it predicts the outcome of the colors and is available as an application in many color management systems. Absolute colorimetry. Absolute colorimetry and relative colorimetry actually use the same table but differ in the adjustment for the white point media.
If the output device has a much larger gamut than the source profile, that is, all the colors in the source can be represented in the output. Using the absolute colorimetry rendering intent would ideally, ignoring noise, precision, etc., give an exact output of the specified CIELAD values.
Perceptually, the colors may appear incorrect, but instrument measurements of the resulting output would match the source.
Colors outside of the proof-print system's possible color are mapped to the boundary of the color gamut.
Absolute colorimetry is useful to get an exact specified color, for example, TaBNWNE, or to quantify the accuracy of mapping methods. Relative colorimetric. The goal in relative colorimetry is to be truthful to the specified color with only a correction for the media.
Relative colorimetry is useful in proofing applications, since it can be used to get an idea of how a print on one device will appear on a different device.
Media differences are the only thing that one really should adjust for, although some gamut mapping also needs to be applied.
Usually this is done in a way where hue and lightness are maintained at the cost of reduced saturation.
By default, in-gamut colors are unchanged, while out-of-gamut colors are clamped. Relative colorimetric is the default rendering intent on many systems. Perceptual. The perceptual intent smoothly moves out-of-gamut colors into gamut, preserving gradations, but distorts in-gamut colors in the process.
Like the saturation intent, the results really depend upon the profile maker.
This is even how some of the competitors in this market differentiate themselves.
The profile maker tries to make results pleasing on this intent.
Perceptual rendering is recommended for color separation. Unsaturation. The saturation intent is designed to present eye-catching business graphics by preserving the saturation colorfulness.
It is most useful in charts and diagrams where there is a discrete palette of colors that the designer wants saturated to make them intense, but where specific hue is less important.
In practice, photographers almost always use relative or perceptual intent. As for natural images, absolute causes color cast, while saturation produces unnatural colors.
If an entire image is in gamut, relative is perfect, but when there are out-of-gamut colors, which is preferable depends on a case-by-case basis.
CMMs may offer options for DPC and partial chromatic adaptation. A black point correction, DPC, is not applied for absolute colorimetric or device link profiles.
For ICCV4, it is always applied to the perceptual intent.
ICCV2 sRGB profiles differ among each other in a number of ways, one of which being whether DPC is applied. Color matching module, also method or system, is a software algorithm that adjusts the numerical values that get sent to or received from different devices so that the perceived color they produce remains consistent.
The key issue here is how to deal with a color that cannot be reproduced on a certain device in order to show it through a different device as if it were visually the same color. Just as when the reproducible color range between color transparencies and printed matters are different.
There is no common method for this process, and the performance depends on the capability of each color matching method. Some well-known CMMs are ColorSync, Adobe CMM, Little CMS, and RGLL CMS. Apple's classic Mac OS and Mac OS operating systems have provided OS-level color management API'(S) since 1993 through ColorSync.
Mac OS has added automatic color management, assuming sRGB for most things automatically in the OS, but applications can explicitly target other color spaces if they wish to.
System-wide color management is used in iOS, iPadOS, and watchOS as well. Since 1997, color management in Windows is available through an ICC color management system, ICM, image color management. Beginning with Windows Vista, Microsoft introduced a new color architecture known as WCS, Windows Color System.
WCS supplements the ICM system in Windows 2000 and Windows XP, originally written by Heidelberg.
Apps need to be aware of color management and tag the content appropriately to accurately display colors.
Otherwise, unlike Mac OS, Windows will display the colors to the maximum extent of the display's gamut, resulting in oversaturated colors on wide gamut displays.
To fix this issue, Microsoft includes a new feature called Auto Color Management since Windows 11 2022. Windows Photo Viewer from Windows 7, also included in later Windows versions, performs proper color management. However, the newer Windows Photos app in Windows 8, 10, 11 does not perform color management until version v 2022.31070.26005.0.
Other Windows components, including Microsoft Paint, Snipping Tool, Windows Desktop, Windows Explorer, do not perform color management.
Unfortunately, the vast majority of applications do not use the Windows color system.
For applications that do employ color management, typically web browsers, color management tend to apply for only images and UI, but not videos.
This is because Windows Media Player API is not color space aware.
Thus, browsers, Chrome, Firefox, Edge are only able to do color management for images but not video.
For the same reason, virtually no video players on Windows support color management, including the default Movies and TV app and VLC, with Media Player Classic Home Cinema being a rare exception. On Android, system-wide color management is introduced in Android Oreo 8.1.
However, most Android phones are shipped with color management disabled. Example, Adaptive Color Profile on Google Pixel, Vivid Color Profile on Samsung Galaxy.
This oversaturates sRGB content to the native display gamut, typically DCI-P3.
Users need to manually select the natural color profile to enable color management, enable an accurate display of sRGB and P3 white color content.
Operating systems that use the X Windows system for graphics can use ICC profiles, and support for color management on Linux, still less mature than on other platforms, is coordinated through OpenICC at freedesktop.org and makes use of Little CMS. Certain image file types, TIFF and Photoshop, include the notion of color channels for specifying the color mode of the file.
The most commonly used channels are RGB, mainly for display monitors, but also for some desktop printing, and CMYK for commercial printing.
An additional alpha channel may specify transparency mask value.
Some image software, such as Photoshop, perform automatic color separation to maintain color information. In CMYK mode using a specified ICC profile such as US web-coded SWOP v2.
Adobe software includes its own color management engine, Adobe Color Engine.
It is also available as a separate color management module, Adobe CMM, for use by non-Adobe applications that support third-party CMMs.
As of 2005, most web browsers ignored color profiles.
Notable exceptions were Safari, starting with version 2.0, and Firefox, starting with version 3.
Although disabled by default in Firefox 3.0, ICC v2 and ICC v4 color management could be enabled by using an add-on or setting a configuration option. As of July 2019, Safari, Chrome, and Firefox fully support color management.
However, it is important to note that most browsers only do color management for images and CSS elements, but not video.
Firefox version 3.5, released in 2011, onwards supports ICC v2 tagged images, and version 8.0, released in 2011, adds ICC v4 profile support.
Version 89, released in 2021, and above apply color management to all untagged images and page elements by default.
Internet Explorer support ICC profiles from version 9 onwards, but only converts non-sRGB images to the sRGB profile, regardless of the actual monitor color space.
Google Chrome uses the system, provided ICC v2 and v4 support on Mac OS, and from version 22, released in 2012. Supports ICC v2 profiles by default on other platforms.
Mac OS versions of Chrome correctly render video.
Safari has support, starting with version 2.0, released in 2005.
Supports v2 and v4 ICC profiles and correctly renders video.
Opera has support since 12.10, released in 2012, for ICC v4.
And TaBNWNE supported ICC v2 from its first release, and v4 since TaBNWNE 20.2, released in 2015. Regarding mobile browsers, Safari 13.1 and iOS 13.4.1 recognizes the device color profile and can display images accordingly.
Chrome 83 on Android 9 ignores the display profile, simply converting all images to sRGB.
As of 2023, Chrome 114, Android Browser 114, and Firefox for Android 115 support multiple color spaces.
The same is valid for their desktop counterparts. Chrome 118, Edge 114, Safari 16.6, Firefox 117, and Opera 100.
In Chrome, when not connected to the internet and an error message displaying "No Internet" is shown on the top, and 8-bit Tyrannosaurus Rex is shown, but when pressing the space bar on a keyboard, mouse clicking on it or tapping it on touch devices, the T-Rex instantly jumps once and dashes across a cactus-ridden desert, revealing it to be an Easter egg in the form of a platform game.
The game itself is an infinite runner, and there is no time limit in the game as it progresses faster and periodically tints to a black background.
A school Chromebook administrator can disable the game. The dinosaur game, also known as the Chrome Dino, is a browser game developed by Google and built into the Google Chrome web browser.
The player guides a pixelated T-Rex across a side-scrolling landscape, avoiding obstacles to achieve a higher score.
The game was created by members of the Chrome UX team in 2014. When a user attempts to navigate to a web page on Google Chrome while being offline, the browser notifies the user that they are not connected to the internet, with an illustration of a pixelated Tyrannosaurus Rex shown on the page.
The game can then be launched either by pressing space or up arrow on desktop, or by tapping the dinosaur on Android or iOS mobile devices.
Additionally, the game can be accessed by inputting Chrome column//Dino or Chrome column//network error/106 into the Omnibox. During the game, the dinosaur continuously moves from left to right across a black and white desert landscape, with a player attempting to avoid oncoming obstacles such as cacti and pterosaurs by jumping or ducking.
Pressing space, up arrow, or tapping the dinosaur on mobile devices will cause the dinosaur to leap, while pressing the down arrow key will cause the dinosaur to crouch.
As the game progresses, the speed of play gradually increases until the user hits an obstacle or a pterosaur, prompting an instant game over. Once the player reaches around 700 points, the game switches from dark gray graphics on a white background to pale gray graphics on a black background, representing a shift from day to night, with daytime sky graphics also becoming nighttime sky graphics.
The color scheme then alternates as the game progresses.
The game was designed to reach its maximum score after approximately 17 million years of playtime, in reference to how long the T-Rex existed before it went extinct during the Cretaceous-Paleogene extinction event. If a network administrator disables the dinosaur game, an error message appears when attempting to play the game, which features an image of a meteor heading towards the player character. The game was created by members of the Chrome UX team in 2014, which consisted of Sebastian Gabriel, Alan Betts, and Edward Yoon.
Gabriel designed the player character, named the Lonely T-Rex.
During development, the game was given the code name Project Bolan in reference to Mark Bolan, the lead singer of the band T-Rex.
The developers chose the dinosaur theme as a reference to the game's function, a joke that not having an internet connection is equivalent to living in the prehistoric ages.
The game was released in September 2014. Initially, it did not work on older devices, so the code was updated and re-released in December of the same year.
The pterosaurs were added as obstacles with a browser update in 2015.
In September 2018, an Easter egg was added to the game in celebration of Chrome's 10th birthday and the game's 4th birthday, with a birthday cake appearing in the desert and a birthday hat appearing on the Lonely T-Rex if the cake is eaten.
In November of the same year, Google introduced a feature to save the player's high score.
The game's source code is available on the Chromium site. In 2021, Google introduced a widget in March for iOS 14, which let players put Chrome column//Dino. A similar widget was introduced to Android later that year.
In July, an Olympic torch Easter egg for the 2020 Tokyo Olympics simulating various Olympic activities was added.
Upon reaching the torch, the Dino transforms into various Olympic games such as swimming, running, and many others.
Instead of the usual cacti and pterosaur obstacles, the Dino now encounters challenges related to the Olympics.
The game received widespread recognition, with the creators revealing in September 2018 that approximately 270 million games were played monthly. The dinosaur game is referenced in the Couch Gag opening segment of the season 34 premiere of The Simpsons, Hades Tortoise. In May 2020, a Microsoft Edge update added Surf, a game where players control a surfer attempting to evade obstacles and collect power-ups.
Like the dinosaur game, it is accessible from an error page when the browser is offline, but can also be accessed at the URL/column//surf.
The game allows for character customization and multiple control schemes. The same year in August, MSCHF and 100 Thieves partnered to create a modified version of the game, titled Dinosaurs, which featured a small arsenal of weapons and time-slowing pills. When mismanaged, the weapons could backfire and harm the dinosaur. We will continue about Google Chrome in part 5.